Hello there, calculus students. This is Mr. Bean. Welcome back for another lesson in calculus, and today we're going to focus on net change. Now, I know Mr. Brust has already taught some of this in the past, so I'm hoping this is a little bit of a review, but we want to make sure we get this down nice and cleanly so you don't have any questions on this. So first off, we're going to make sure you know that whenever you see some type of rate of change, if you take the integral of a rate, you're going to get net change. If you integrate a rate, you get net change. So if I was in teaching you live in class, I would remind every single time I saw an integral and there was some type of rate of change, I'd always be reminding you, hey, integrate a rate, you get net change. Now, if we're talking about some type of position on an x or y axis or velocity of some sort, a lot of times we'll call this displacement. Sorry, sloppy handwriting. Displacement. Now, displacement is just the same thing as saying the net change from where it began to where it is at the end point. Make sure you've got that written down. I'm going to move on here to our first example. Number one, Mr. Brusty's going to drive across town to Mr. Sullivan's house to play with some Star Wars. We've come up with a equation here, function that represents his velocity. Now, this is a made-up thing, all right? But the important thing is to know that it's not miles per hour, it's miles per minute. Now, that's important because we're only measuring by minutes over the first 30 minutes. The scale here is your window and your scale. This is 5 minutes, 10 minutes, 15, 20, and so forth. So what we're trying to do is set up an expression for each of these scenarios, and then we'll just use a calculator to solve it. So how far is Mr. Brust from his house after 10 minutes? The way you do that is we just want to see what's the net change from the beginning to end. So if we go from 0 to 10 minutes and integrate the velocity, we are going to get, I should probably add a little dt here, and then it's going to be approximately, now we can plug this whole thing straight into the calculator. Let's see what we get. Pull up my calculator, go to my y equals. I have already plugged this in already to kind of save myself some time. I want to double check my mode. It is in radians. Yes, it is. Second quit. So now I say math 9. So I'm doing my integrals and I'm going from 0 to 10 minutes. Now, instead of plugging in this whole thing of sine 0.3t and so forth, I can just use my variables button because I plugged it into the y variables and then the function, and the very first option is y1. That's where I plugged it in. So if I just pull that up, it's going to save me a little bit of time here. And then with respect to x. So hit enter, and what do I get? It's thinking. You can see its little spinning thing right up there. 3.010. So I can just say 3.01. So I come back here. 3.01 miles. In the first 10 minutes, it's been 3.01 miles how far I am away from my house. Now, what in the world is happening here? This portion is negative. Okay, that is negative. This portion, up until we get to 10 minutes, so I'll draw the line here and stop it. This portion is positive. So what's happening is that this is going away from the house. Mr. Brust is traveling away from the house in the negative direction, so away from Mr. Sullivan's house. This is in the positive direction, going towards Mr. Sullivan's house. So it's starting at 0, subtracting the negative, adding the positive, and that's how we get the net change of 3.01. All right, let's do another one. How far is Mr. Brust from his house after 15 minutes? So now we're going to go from 0 to 15 of that velocity function. And that is approximately, let's pull up the calculator, and we just do the same thing. Let's do this. Second entry. And then it just pulls the whole thing up. And I just have to scroll back here and change the 10 to a 15. Right? Yep. And then just hit enter. 3.397. So this is approximately 3.397 miles. So why is it barely more after 5 more minutes? Because, watch, now we're going all the way to 15. So we add this bit here, but then you subtract this bit. because this is negative. So that's why it used to be 3.01 miles, and 5 minutes later, we've hardly gone any further because we somehow, Mr. Brust turned around and went the wrong direction again. Okay, so that's what this negative is. All right, if Mr. Brust arrives at Sullivan's house after 30 minutes, how far away does he live? So how far apart are they from each other? So that is just a simple 0 to 30 of v of t. So what is the distance, the displacement between their houses if it takes 30 minutes to get there? Let's do the same thing again. Second entry, and let's change that 15 to a 30 and hit enter. 22.824, 22.824, 22.824, whoops, 24 miles. That is how far apart they live because we're just taking the displacement from 0 to 30 minutes. How many miles, should say Mr. Brust, how many miles did Mr. Brust drive? So now this is a little trickier because what we want to include on this is everything. So how far is this? Plus how far is this? Plus how far is this? Plus how far is this? We're going to add up everything. So these negatives need to become positive. The way you do that is we're going to put some absolute value around it. So let's plug this in. We're going to go from 0 to 30, but this time we want the absolute value of v of t dt. Okay, so this is how we set that up, and then we're going to say that is approximately. Okay, so how do I do that? Let's go second enter again. But now, oh, let's see here. Y1, we need to put second catalog. Second catalog, the very first option is absolute values. Absolute value. Now I need the Y1 there. So variables, Y variables. First option is function and Y1. Now I've got my velocity function in absolute value brackets. 28.497. Let me just click and drag this over here because I might forget. 28.497. So 28.497 miles. So you can see here there was an extra, what, 5.5, 6 miles driven in the wrong direction. That's the total. So what that tells us is the absolute value would take this graph and flip it up on top. So it's just taking the total area of all of these things, which I know you've done already, but that's just fitting it into these word problems. Okay, that leads us to this next point. If you take the integral of velocity, you get displacement. If you take the integral of the absolute value of velocity, it is equal to the total distance traveled. Total distance. Now don't get this confused with when we take the absolute value of velocity. If you just take the absolute value of velocity, you get speed. If you take the absolute value of velocity and integrate it, you get the total distance traveled. All right, get those down. Pause if you need to at this point. Example 2, particle's velocity is given by blah, blah, blah. If x of t represents the position of the particle along the x-axis, find the following. So we're going to find the position of the particle after 3 seconds. So if we want to know after 3 seconds, we need to know how far it has traveled in those 3 seconds. So set this up like this. We're going to go from 0 to 3 of v of t. In this case, because we're going to do it by hand, let's go t cubed minus 2t squared plus 1 with respect to t. Okay, this will tell us how far it's traveled, or its displacement, I should say. It's going to give us the displacement where its position is after 3 seconds. But we need to take where it started, which was 5, and add it. Okay, so that is extremely important. We're going from 5 seconds is where, or excuse me, if the position is 5, so we start there, and then this integral represents the displacement over a 3-second period. So here, let's go to the next part here. We have 5 plus, open parentheses, t to the 4th over 4 minus 2t cubed over 3 plus t, and then we're evaluating from 0 to 3. All right, now let's plug stuff in. So 5 plus, I'm going to do a bracket here, plug the 3 in. So 3 to the 4th is 81. force minus 3 cubed is 27, but then I'm going to divide by 3 and get 9. So this is 2 times 9 plus the 3. All right, so there is the 3 plugged in, minus, now if we plug the 0 into all of this, you just get 0. Okay, now after a simplification process here, we're going to get, so let's see, I have 5 plus 81 fourths, 18, negative 18, plus 3, negative 15. So 5 minus 15 is negative 10. 81 fourths minus 10 is the same thing as minus 40 fourths. So then our final answer is 41 fourths. That is the position of this particle after 3 seconds. We started at 5, and then you add the net change. Okay, what's the position of the particle after 2 seconds? So here's how we do this one. If we want to know after 2 seconds, then we're going to go from, well, what do we know? We know that at 1 second it was at negative 2. So let's do this. We're going to start at negative 2 and add, so this is the position, negative 2, and then we're going to add displacement between 1 second and 2 seconds. Because if we know at 1 second it was at negative 2, then this would give us, so v of t, I'm going to save myself some time instead of writing that whole thing out, d of t. So what does this mean? You can go like this, negative 2 plus, now we already took the antiderivative here, so you can just go straight to t to the 4th over 4. I'm going to fast forward this a little bit more. And evaluate from 1 to 2. Move my screen down so you can follow a little bit more. Okay, negative 2 plus, plug in the 2. Minus, now we plug in the 1. Okay, you're probably running out of room here, so I'm going to draw a little arrow, bring that stuff up here. And this whole thing, I've already done this workout, so this whole thing is going to simplify down. If you add up all the fractions, you're going to get negative, 3 fourths. Negative 3 fourths is our answer for this. That is the position after 2 seconds, if after 1 second it was already at negative 2. For the next example, we're going to take a velocity function here and figure out how far we've gone for the total distance, but this time we're not going to use a calculator. So for the first example, I used a calculator. This time, we're not. Well, the problem is most of these problems I'll give you in the practice will not have a graph with it. So yes, we're going to go from the first 4 seconds, so here, from 0 to 4. So I've got this area here, and then I've got this area here, and I have to figure out those areas and take the absolute value. So really, whatever they are, make this one positive, add them together. Well, if you don't have the graph, you have to figure out when this thing, negative 2t plus 3, when this velocity, or the rate of change, whatever function it is, when does it equal 0? Because that's going to be where it's crossing the x-axis. So let's subtract a 3, divide by negative 2, and we'll get 3 halves. So when t equals 3 halves, which is right there, that's when it's going to equal 0. So what you'd have to do is this. I'm going to take from 0 to 3 halves of negative 2t plus 3, and then technically dt. And then the other one I'm going to figure out is, I'll do this one down here. I'm going to go from 3 halves up until 4 seconds. And then of negative 2t plus 3 with respect to t. Okay, so let's do this. Negative 2t squared divided by 2 plus 3t. We're going to evaluate that from 0 to 3 halves. And then we'll do the same thing here. So I'm going to simplify this. I get negative t squared plus 3t. Evaluate from 0 to 3 halves. This one will be a negative t squared plus 3t. Evaluate from 3 half. Sorry about my t's and my pluses. They look identical there. I got to be careful. T.
evaluate from 3 over 2 to 4. Okay, so let's plug this in. I get a negative 3 halves squared is 9 fourths plus, and then 3 halves times 3 is 9 halves minus, now we plug the 0 in and I just get a 0. So negative 9 halves, negative 9, not halves, fourths plus 18 fourths. Let's get common denominators. That's going to equal 9 fourths. All right, so this one right here equals 9 fourths. That's important. I'm going to circle this one to remind me to come back to that. Let's try this here. So plug in the 4. I'm going to get a negative, and then 4 squared is 16, plus 3 times 4 is 12, minus, now we plug the 3 halves in, which we already figured out. When we plugged in the 3 halves here, we got that it was 9 fourths. So that makes this a little easier. 9 fourths. So this is negative 16 plus 12 is negative 4. Negative 4 minus 9 fourths, which gives me negative 16 fourths minus 9 fourths. That comes out to be a negative 25 fourths. All right, so there's my two values. This one is a positive 9 fourths. This is a negative 25 fourths, but I have to take the absolute value of this one. So really, my final answer then is 9 fourths plus 25 fourths, which gives me 34 fourths. Is there any units that I need to worry about? Seconds, particles, velocity, function. Nope, there's no units, so 34 fourths. There is my answer there. So again, the reminder here is, if you were trying to write yourself some generalization, some notes, is take the velocity function or the rate of change function, set it equal to 0, because you need to know when is it crossing the x-axis. Then you've got your boundaries for these two integrals that you're going to work with. All right, last example. This situation, it's kind of similar to what we've already done. When you have a derivative function, and they want to know what is h of something, the original function, all you need to know is one other point of the function. So if we have h of negative pi, and we know it equals 12, then what we can do is we say 12 plus, it's just like the example from number 2. We're going to start off at 12, and we're going to add how much it changes between negative pi and 3 pi over 2. 3 pi over 2. And then we take the derivative, or excuse me, the integral of the derivative cosine of t with respect to t. Okay, what is that going to be? 12 plus the integral of cosine of t is just a sine, and it is positive because the derivative of sine is cosine, so that works. And then we're going to go from, and we're only concentrating on this portion of it when we plug in these values, from negative pi to 3 pi over 2. All right, so now we go 12 plus, plug in sine 3 pi over 2 minus sine, plug in a negative pi. So this is 12 plus sine of 3 pi over 2, that is negative 1, minus sine of negative pi, that is a 0. So it's 12 minus 1, 11. H of 3 pi over 2 equals 11. Okay, so similar to what we've already done, again, it's just integrating this derivative to help us figure out how far it's moved from negative pi to 3 pi over 2. And that is the end. This is a pretty important lesson. I mean, I know we say all of our lessons are important, but this is stuff you're going to see quite a bit on the AP exam. So you really want to get a good, strong understanding of the net change versus the total change and how to integrate a rate and what that means. All right, good luck on the practice, and I'll see you back in Unit 11.